Hi, welcome back to another video. So for today's video, we have the following function. Capital J of A is equal to the integral from 0 to infinity of e to the negative x squared multiplied by cosine of 2ax dx, for a can be some real number. So let's actually get started. So first thing, let's actually define our definition of our function cosine of x in terms of a complex value function with an exponential function. So note that cosine of our, I'm going to say a in this case, since our function j is in terms of a, is equal to e raised to the I times a, then plus e with the power of negative I a divided by 2. Okay, so we have that definition in terms of a complex exponential function. So let's actually replace a with our new input 2ax. So that's pretty straightforward. So just replace all your inputs for a in terms of 2ax. So we have is equal to e raised to the I 2ax, then plus e to the negative I 2ax, then divided by 2. Okay, nice. So now that we have that, we can actually just substitute our complex exponential value into our for our new integral. So that means j of a is equal to the integral from 0 to infinity, and well, okay. So there's a this is divided by 2, so 1/2. So I can actually just move that outside the integral. So this is 1 over 2. Then the integral from 0 to infinity of, okay, so they share the same base with e and then the power of negative x squared, so I can actually just use our rules for exponents with the same base and combine them. So this means negative x squared, so distribute to here, so that means this is e to the negative x squared and plus I to ax, then plus e to the negative x squared minus I to ax dx. And now with that, let's actually simplify this out. Specifically, let's actually simplify our powers, both these terms here. So negative x squared plus I to ax. How about instead I actually move the I to the right, so our 2's in front. So instead I have 2aix and then negative x squared minus 2aix. Right. Okay. So now let me actually just factor out the negative. So we have negative multiplied with x squared, then minus 2aix, and then minus x squared plus 2aix. So I'm actually going to do for our inside parentheses for both is I'm actually going to add and subtract an a squared. So negative x squared minus 2ax minus a squared plus a squared, and then equals same thing, negative x squared minus or plus 2aix minus a squared plus a squared. I just want to make sure I actually have plenty enough room to show the rest of the work later. So notice that our first three terms, this is actually a perfect square. So we can rewrite this as negative x, and this is minus ai squared. You can check to see, so x times x is x squared, x times negative ai, and then do it again a second time, so this is minus 2aix, and then if you multiply negative a times I, and again, so negative ai is multiplied by negative ai again that's positive a squared multiplied by I squared. I squared is negative 1, so you get negative a squared. And then this is plus a squared. Okay? And now, same reasoning for here. So this is negative x, this time this is positive, plus ai square, and plus a square. Okay, then we can actually just distribute our negative. So we get the following, x minus ai square minus a square, and then minus x plus ai square, then minus a square. Okay, now we have that. Let's actually plug our new simplified expression back into our integral. So now we have the following just rewritten. So the integral from -1/2. And notice that if I were to put back the simplified expression of our powers back to here, they actually share the same constant because it's basically e raised to the -a square for both terms here. So this means we can factor out e to the -a square outside of the integral. So e to the -a square, and then multiply by the integral from 0 to infinity of, let me write this in parentheses. So this is e to the negative, let me see, this is, yeah, negative x minus ai square, and then plus e to the negative x plus ai square, then dx. Okay, and with that, we can actually use our properties of integrals and actually split them into two integrals of the same bounds, but different functions we're integrating with. So in terms, this is 1/2 e to the -a square. I'm gonna put brackets for here. So this is from 0 to infinity of e to the negative x minus ai square dx, then plus the integral from 0 to infinity of e to the negative x plus ai square dx. Okay, cool. So now what I want to do is we actually need to calculate these integrals here. So how about instead, let's actually define these integrals. So using my black marker, how about we're going to let the integral from 0 to infinity of e raised to the negative x minus ai square, why don't we let this integral be defined as j sub 1 of a, and then the integral from 0 to infinity of e raised to the negative x plus ai square, let that be defined as j sub 2 of a. So that means let's actually focus our j sub 1a. So j sub 1a, almost wrote an I. So that means our j sub 1a is equal to the integral from 0 to infinity of e raised to the negative x minus ai squared dx. Okay, now let's actually do a substitution. So how about we let p equals x minus a sub I. Okay, so if you haven't caught on by now, we're actually doing a u substitution. So that means dp is equal to let's see, that's dx. Okay, so now don't forget what this means is that we actually need to change our bounds of integration as well. So find our new integral. So that means when x equals 0, so that means p is equal to negative ai, and then when x is equal to infinity, that means p is infinity. And then let's see, it's just e to the negative p square of dp. Okay, so that's our j sub I. And now again, for j sub 2, it's just the same method as before. Let's see, integral from 0 to infinity of e to the negative x plus ai squared dx. Okay, then I'm gonna this time let q equals x plus ai, then dq is equal to dx. Then our new integral is, so as x approaches 0, then that means our new bound in terms of q is ai, and then infinity, so that's infinity. And then we get e to the negative q squared dq. Okay, now the next couple steps, now the rest of the steps I should say, we're gonna need to define the following. So we note that the error function of x is equal to the following. So this is the definition of this function. It's defined as 2 divided by the square root of pi from 0 to x of e to the negative t square and dt. Okay, so let's say now, because that our upper bounds is because we're going to manipulate this eventually later, so we're going to let x approaches infinity in this case. So that means as x approaches infinity, yeah, I can write space here, as x approaches infinity. So that means when x approaches infinity, x has to be the upper bound, so infinity. So 2 over the square root of pi from the integral from 0 to infinity of e to negative t square. So notice that if you recall from like many videos ago, this is actually very similar to the formulation of the Gaussian integral, but since this is from 0 to infinity, it's over half of its area of the Gaussian integral. So from the results from the Gaussian integral, when it's defined over the intervals from negative infinity to infinity, is actually equal to the square root of pi. But since this is defined by half of that, specifically from 0 to infinity, is divided by 2, so that means it's equal to the square root of pi divided by 2. So this integral defined here specifically is equal to square root of pi divided by 2. But then you multiply 2 over square root of pi, those terms cancels. That means our error function for this, the error function at infinity, I should say, is equal to 1. And another property we want to state in order to help manipulate to solve these two integrals here is we're also going to note the following property. So if we have our integral from a to b of f of x dx, we can actually split this into two integrals with adjacent intervals. Specifically, if a is less than c less than b, so that means with this integral given from a to b of f of x dx is equal to a to c of f of x dx, and then plus the integral from c to b of f of x dx. That's actually what we're going to use in order to calculate these two integrals here. Okay, nice. So then that means 2 to the square root of pi from 0 to infinity of e to the negative t square is dt is equal to 2 divided by the square root of pi from 0 to x of e to the negative t square dt, and then plus well, I meant to write 2 divided by square root of pi. 2 divided by square root of pi from x to infinity is equal to e to the negative t squared dt. Okay, which is equal to 1. Okay, so with that, we're trying to solve that. We can actually subtract our 2 square root of pi of the integral from 0 to x e to the negative t squared dt, which is actually the error function. So in other words, this is this is let's see, keep writing integral first. It's actually supposed to be 2, did it again. So it's supposed to be 2 divided by square root of pi, and the integral from x infinity e to the negative t squared dt, which is equal to 1 minus the error function of x. Now with that, then that means we can actually just divide 2 square root of pi divided by the square root of pi. So simplify this out, we actually get the square root of pi divided by 2, then minus the square root of pi divided by 2 multiplied by the error function x. Okay, so we actually figure out what we're supposed to do now, because now that we have our bounds, we have the following standard formulation, so we can just plug in our bounds for negative AI and then positive AI. So therefore, that would have to mean j sub I, or j1 sub a, sorry, is equal to, so we have negative AI, so we have the same standard formula for solving, so we can just plug negative AI in terms of x, in place of x, excuse me, pi divided by 2 minus square root of pi divided by 2 error function of AI, and then j sub 2 of a is equal to same thing. So what do we have? Actually, this is supposed to be negative AI. My bad. So this is negative AI over here. While over here, this is we plug in for positive AI. So square root of pi divided by 2 minus square root of pi divided by 2 error function of negative AI. Now all we have to do left is just calculate our j sub 1 and j sub 2, so add our j sub 1, j sub 2 over here. So therefore, j sub 1 a, and then plus j sub 2 a is equal to square root of pi plus square root of pi. So that means it's 2 square root of pi divided by 2, which is just square root of pi, and then plus, so that means minus. So that means I can factor out minus square root of pi divided by 2 of the error function of a negative AI, and then plus the error function of AI. Okay, cool. Now, one last thing we want to note is that I want to prove this note as well. So hopefully I got some room to prove this note here. So we actually want to note, actually let me write this in a different color and prove it with a different color. So let's actually use the color red for this. So note that, let me see, make sure I'm not writing on the light. Okay, right here's good. So note is that the error function of negative x is equal to negative 1 times the error function of x. So what this means, that the error function is actually an odd function, and I'm actually going to prove this property. So the proof is that, so we're given our definition of the error function of x. So the error, in this case, let me say it this way. So we have our definition of the error function. So this piece specifically, let me underline this. So error function x equals 2 divided by square root of pi, integral from 0 to x of e to the negative t squared dt. Okay, so now let's actually plug in our input for negative x. So this would mean only the upper bound would be negative x. So this is equal to 2 divided by square root of pi, and then the integral from 0 to negative x of e to the negative t squared dt. Okay, now next thing I want to do is let's actually do a u-substitution. So let's let t equals negative s. Okay, then that has to mean dt is equal to negative ds. The Nintendo DS, get it? Okay, and anyways, that means we substitute. So rewrite negative, or 2 divided by the negative 2 divided by the square root of pi. Then our bounds specifically is from 0 to first, before I do anything, let's actually calculate our bounds. So that means st is equal to 0, then that means s has to equal 0. Then st is equal to negative s, then s has to equal, so we have negative s, so that means negative x, so that means this would have to equal x, or yeah, x. Then that means e, and then replace this with negative, minus, and then inside is supposed to be negative s square, and then negative ds. So let me put ds here, and I'll put a negative outside here. Fix that. Just look, the placement looked just off by a little bit. So mine equals negative 2 divided by square root t. Okay, and then negative x squared. So that means this is just equal to negative 2 divided by square root of pi. Bounds from 0 to x of e, and then negative s squared. It's just positive x s squared, then ds. So therefore, this is actually equal to the negative error function of x. Okay, so we just showed that this is an odd function. So with this property, we can actually state that the error function, let me write a star for here. The error function of negative ai is actually equal to the negative error function of ai. Okay, so with that means, let me put this in red as well. So error function of, that means error function of negative ai, so replace this with here, so it's negative error of ai, and then plus error function of ai. This is just equal to 0. So that means, pull out my black marker again, all we're left with is that j1 of a plus j2 of a is just equal to the square root of pi. Okay, great. So then now that we have that, let me actually rewrite what we have from before. So arrow, that means 1/2 e to the negative a square of j sub 1a plus j sub 2a is equal to, so replace j sub 1a plus j sub 2a with square root of pi, and so we get that this is just the square root of pi divided by 2 e to the negative a square. And so that's the following. That means, I'm going to rewrite our conclusion in black one more time. That means, therefore, I'm not going to write the j of a again a second time, I'm just going to write the integral instead. Rewrite the integral. So therefore, our integral 0 to, hold on, let me rewrite that. It looks a little crooked. So our integral 0 to infinity of e to the negative x squared cosine of 2ax dx is equal to the square root of pi divided by 2 multiplied by e to the negative a squared, like so. Ooh. Nice, that's pretty cool right there.